On December 27, 2004, a sudden, massive surge of energy slammed into Earth and highly charged our upper atmosphere. Telescopes tracked this anomaly back to a single star called SG 18062, sitting 50,000 light-years away on the far side of the Milky Way. In just 0.2 of a second, that single distant star released more energy than our own sun will produce in 250,000 years. Even traveling from halfway across the galaxy, the flash arrived brighter in gamma rays than a full moon. We survived that hit entirely because of the vast space between us and the source, which leaves an obvious question. What happens if an eruption like that goes off closer to home? That blast came from a magnetar. A magnetar is a hyperdense, crushed dead star packed into a sphere only about a dozen miles across. What defines them is their localized magnetic field, which is a staggering 1 quadrillion times stronger than Earth's. Every so often, the rigid crust of the star undergoes a microscopic shift. That tiny twitch within such an extreme magnetic field acts as a trigger, launching an unimaginably powerful flare of gamma rays out into space. The energy output from these flares is absolute. If a magnetar fires in our direction, the only variable dictating our survival is the physical distance between us and the star. To test that variable, let's bring Earth in close and imagine we are sitting just 1,000 miles away from a magnetar. At this proximity, the radiation wouldn't be what kills you. The immediate threat is the mechanical violence of the magnetic force itself. The directional pull is so overwhelming that it would instantly drag every atom in your body out of its normal alignment. At extreme close range, the magnetar acts as a molecular meat grinder, rewriting the basic rules of chemistry and biology before you even realize what hit you. Now, let's pull back to a distance of 10 light-years. We are far outside the range of that magnetic shredding, but we hit a distinct planetary threat. At 10 light-years out, the lethal danger comes entirely from the resulting gamma ray burst hitting the planet. Gamma rays are a highly energetic form of light. They are invisible to human eyes, but they are incredibly interactive with atmospheric chemistry. When that light arrives, an intense wave of gamma ray energy violently overwhelms our upper atmosphere. This causes immediate chemical destruction, burning the protective ozone layer completely away in a single devastating pulse. A magnetar strike at this distance doesn't physically crush the planet. Instead, it systematically uninstalls our radiation shield in a matter of seconds. In the immediate aftermath of the strike, the Earth is physically intact. The ground is still there, the oceans remain, but our primary biological defense mechanism is gone. This NASA map shows total atmospheric ozone levels, focusing on regions of extreme vulnerability. Without that protective layer, Earth's surface is exposed to unshielded radiation. Within months, this heavy radiation exposure would expand across the entire globe, killing every living thing on the surface. A magnetar flare acts as an invisible extinction-level event. It leaves the world looking completely normal, while quietly sterilizing the surface. Today, astronomers are actively tracking roughly 30 known magnetars sitting inside our own Milky Way galaxy. Some of these local magnetars are positioned much closer to Earth than the star that caused the massive 2004 energy surge. And the core behavioral problem with these dead stars remains. They twitch and flare entirely without warning, producing no identifiable buildup. Because the resulting gamma ray burst travels exactly at the speed of light, no telescope or instrument on Earth can see it coming before it actually hits. If a nearby magnetar twitched 10 years ago, the resulting energy pulse is already in transit. We simply won't know it's coming until the very second the sky changes.